This is a 3.5-inch touchscreen built for the Raspberry Pi 5, and today I am turning it into a standalone internet radio player that connects to any Bluetooth speaker. I built this because paying a monthly subscription to Spotify just to listen to music in your own home is a complete waste of money. Buying streaming subscriptions is a tax on people who do not understand technology. Today, I am cancelling Spotify, and I am going to show you the exact design process I used to make this device so you can build it yourself for a fraction of the cost. A lot of people build music players using expensive e-ink displays. I've seen projects using a $60 5.7-inch e-ink screen just to show cover art. That is a terrible idea. E-ink takes up to 30 seconds to refresh. By the time the screen updates, the song is already half over. Instead, this device uses only 3 parts, a much faster Raspberry Pi 5, a cheap 3.5-inch XPT2046 touchscreen, and a standard Bluetooth speaker you probably already have sitting in a drawer. The brains of this project is the Raspberry Pi 5. It is incredibly powerful, overkill for a simple radio, but it guarantees 0 lag when navigating the interface. To use it with the touchscreen, I just aligned the GPIO pins and pressed it right onto the board. No complex soldering required. Let us look at the design iteration of the 3D printed enclosure. I made several different versions in Fusion 360 before I was fully satisfied with the result. The first design was very basic, but gave a good rough draft for the overall look that I wanted to achieve. You can see in the model that it has 2 parts with cutouts for the display and a hole for the cable to slot through. However, I realized quickly that designing a case blindly leads to terrible tolerances. I went back to the drawing board and decided to make a completely new Fusion 360 project. This time around, I actually imported the exact 3D models of the Raspberry Pi 5 and the 3.5-inch touchscreen directly into the workspace. Having all of these components in one project made designing the enclosure much easier. I was able to actually design around both the screen and the Pi to ensure that everything had proper dimensions. There were a few key changes in this design compared to the first. I added a slot on the back to properly route the power cable through the back. Additionally, I decided to make this design a snap-fit case, so absolutely no screws were necessary in the build. In order to do that, I added these angled joints in the model. I also added standoffs for the Raspberry Pi to hold it securely in place in the enclosure. Overall, this second design was much more professional looking and the project was really taking shape. I then decided to make smaller adjustments in the third version of this design. In the second version, there were only 2 snap-fit joints and I wanted to add 2 more to this new design. Additionally, I made the enclosure slightly thicker to improve the overall structural integrity. Lastly, I made minor modifications to the dimensions to improve the tolerances between the enclosure and the touchscreen bezel. Now, I'm going to show how to set up the software on the Raspberry Pi to get it to stream internet radio and display the touch interface. The beauty of internet radio is that it gives you music 24/7 absolutely free, and with the right code it works flawlessly without dealing with broken APIs or developer tokens. The first step in setting up the software is to flash a micro SD card with the Raspberry Pi OS on it. In order to do so, I used the Raspberry Pi Imager software. I always click the settings icon before writing the image to the SD card. This allows me to enable SSH to remotely access my Raspberry Pi and to connect it to my home network. Then I click write and wait for it to finish. Now that the base operating system is imaged onto the SD card, I am booting directly into the standard Raspberry Pi desktop environment. Because nothing is configured yet, the initial video output is routed through the standard HDMI port, which you are seeing on the screen right now. Once the system finishes its initial setup, I need to install the drivers for the touchscreen. Fortunately, this specific screen model is very well known in the Raspberry Pi community, and there are highly reliable drivers readily available on GitHub. First, I clone the repository directly from GitHub. Next, I set the correct directory permissions and execute the installation script. This script automatically compiles the drivers and configures the system to route all graphical output to the touchscreen. After a successful compilation, the system reboots, and just a few seconds later, the desktop appears flawlessly on the new 3.5-inch display. Now that the mini display is fully configured, I'm switching over to a standard SSH client to connect the Bluetooth speaker. Using the Bluetooth CTL command, I scan for available devices, locate my speaker in the list, pair them, and enable the trust setting. Enabling trust is crucial. It forces the Raspberry Pi to connect to the speaker automatically every time it reboots. The final step is executing the connect command, which automatically configures the system to route all audio output directly to the Bluetooth speaker. To verify that the connection is working, I am using a lightweight console media player called MPG123. First, I install it directly from the repository using the apt install command. Once the installation is complete, I execute a test MP3 file. The audio plays back flawlessly. Now that the Bluetooth speaker is connected and tested, we need to engineer a lightweight keep alive script. This prevents the speaker from entering sleep mode or powering off if the radio player is ever paused. The logic is straightforward. It runs an infinite loop using the Bluetooth ctail command to constantly monitor the connection status. If it detects that the speaker has dropped, it immediately forces a reconnection. I will leave the exact code for this script in the pinned comment below. All you have to do is replace the placeholder with your speaker's specific MAC address. Once the script is written, I modify the permissions to make it executable and run a test sequence. Assuming there are no syntax errors, it is critical to manually verify how the connection query executes, as terminal outputs can vary between OS versions. I copy the commands from the script directly into the terminal to ensure they execute without errors. The specific output we are looking for is connected yes. This is the exact string the script is searching for. If it fails to detect this string, it instantly initializes a new connection. With the Keep Alive script fully tested, we need to verify the Python graphical environment. I prepared a test script called demo.py. This is a lightweight duck hunt minigame designed specifically to test the display rendering and calibrate the touch panel. To execute this script, we must configure two system files. The first is .x initrc. This file dictates exactly what executes when the graphical X server initializes. Because we do not want to waste system resources on a bloated desktop environment or window manager, we bypass it entirely and declare our Python script as the primary graphical application. Inside this file, we also disable display power management to prevent the screen from ever entering sleep mode. Next, we initialize our Bluetooth Keep Alive script in the background. Finally, we inject a specific dbus configuration. This step is crucial. It ensures that our graphical applications can seamlessly communicate with the internal message bus, allowing them to route audio properly and respond to physical button presses directly from the Bluetooth speaker. I will provide the exact contents of this .x initrc file in the pinned comment below. The final file we need to modify is the shell profile. We must force the system to automatically initialize the graphical X server the moment it boots into text mode. This X server will then seamlessly hook into our .x initrc configuration. Now that the architecture is built to launch Python graphical applications instead of a desktop environment, I reboot the Raspberry Pi. After a fast boot sequence, the Duck Hunt script launches perfectly. The display renders in full color, pushing roughly 15 frames per second in this game mode. Stylus inputs are registered accurately and the touch calibration is flawless. Now for the final execution, we replace the test game with the actual internet radio application. Here is the custom Python script. It operates on a very simple logic. Inside the stations array, we define the exact radio streams we want to listen to. The first field dictates the button labels, in my case simply 1, 2, 3 and 4. The second field is the station name that will display at the top of the screen, followed by the direct URL of the MP3 stream. To extract these direct URLs, you bypass the web players entirely. Go to directory.shoutcast.com, select a station and download the playlist file. If your browser tries to open it in a new tab instead of downloading, simply view the page source using Ctrl+U and copy the raw stream link. Next, the script defines the graphical environment parameters, a strict 480 by 320 pixel geometry, forced full screen, a neutral grey background, and the mouse cursor is completely disabled to keep the UI clean. We then initialize the header text and the status bar. Below that, the code maps out 4 specific touch zones on the screen to control the radio playback. For audio control, I wrote a set_volume function. Instead of dealing with weak software volume limits, this function communicates directly with the Bluetooth driver using the WPCTL system command to adjust the actual hardware volume. Next, we need a function to pass the stream metadata and push it to the status bar. This typically extracts the current song title or the radio show name, though it depends entirely on what raw data the specific station chooses to broadcast. Finally, there are a few utility functions to refresh the UI status and cleanly terminate playback. As always, I will leave the complete source code for this application in the pinned comment below. Now we copy this Python code directly into a new file named radio.py. To ensure it executes automatically on boot, we open the .xinit rc configuration file and swap out the duck hunt test script with our new radio.py application. With those changes saved, I initiate a clean reboot of the hardware. We wait just a few seconds for the Raspberry Pi to load the operating system and launch the script. And here is the final result, a clean, fully functional graphical user interface for our standalone internet radio player. I lower the volume slightly using the touch controls and test switching between the radio stations. The streams load instantly and the touch interface is incredibly responsive. People spend hundreds of dollars on dedicated streaming devices or lock themselves into $10 a month subscriptions for the rest of their lives. Over 10 years, that is over $1,000 just to rent access to music. By utilizing open source internet radio streams, you have access to thousands of stations globally, categorized by every genre imaginable at zero cost. The audio quality is fantastic and you own the hardware. You are not relying on a company to keep their servers running or update their app. If Spotify decides to change their API tomorrow, every single DIY Spotify player on the internet will instantly break. This internet radio player will keep working decades from now. You now have a fully functional, standalone internet radio player that runs 24/7 for pennies and requires 0 monthly fees. The touchscreen is responsive, the PETG case is indestructible, and the Bluetooth audio is crystal clear.